So I made a quantum computer in my last video. You don't have to watch that video because I'll try and explain what this does as I go. But when I was making that video, I realized that my quantum computer seems to be working kind of well enough that I could actually use it for a computation. That is really surprising. I didn't expect it to be this good, to be honest. So I thought it would be so cool to show you a quantum computation in action. And I hope that by showing you that, you'll get an idea of what it exactly is that quantum computers can do well and what they can't do well. Because one thing I'm absolutely sick of as a person who, used to research quantum computing is people telling everyone in the media that quantum computation is going to solve all the world's problems. Quantum computers are supercomputers. They're really not. Quantum computers are usually worse than normal computers. Worse in the sense that they're about the same, but they're way harder to build. But there's some situations where we have an algorithm for how to use the quantum computer that lets it do something that would be basically impossible on a regular computer, as in would take a really, really long time. So the classic example is factoring prime numbers. On a regular computer, that takes a really long time for even 30-digit numbers. And that's an important problem because all of our encryption currently relies on that problem being really hard for hackers to do. But on a quantum computer, people discovered an algorithm that would let you do it quite quickly if you did have a working quantum computer. And I think that since then, there has been this idea that we will find lots of algorithms to do useful things on quantum computers. And by and large, it hasn't really panned out. It's been almost 30 years since the factoring algorithm came out, but somehow, while I was editing this video, a new polynomial time quantum algorithm was discovered. Finally. I'll talk about that result and how significant or not significant it is another time, but let's get back to this video. I want to explain why it's so difficult to make a quantum algorithm good. So the thing with my quantum computer is that it is a 1-qubit quantum computer, literally as useless as it gets in terms of quantum computing. So I have to think of an algorithm that will be possible on this useless machine. And luckily, there kind of is one. It's actually kind of my favorite algorithm to teach people because it really demonstrates what quantum computers do. It's called the Deutsch-Jozsa algorithm. Richard Jozsa is actually my PhD supervisor, and he gives a great explanation of this algorithm and how it shows what quantum computers can do well. So I'm going to try and pass on that same intuition for you. I've just got to try and figure out how using the equipment that I have. So it's an experiment for both you and me. Okay, let me explain the problem that the Deutsch-Jozsa algorithm is trying to solve. Suppose you're approached by this shady character who wants you to solve a riddle. He has a computer in this black box doing some sort of mysterious calculation, and you can send in a 0-bit or a 1-bit into the computer as an input, and then it will return 1 bit as an output. So for example, you can send in a 0 and his computer will send out maybe a 1. In this riddle, he's going to ask you to find out something about this secret function his computer is calculating. If that sounds like a completely ridiculous made-up problem, that's because it is. The reason that the Deutsch-Jozsa algorithm was made to solve that problem is because it's the most obvious problem to solve with a quantum computer, not because it's a problem you would want to solve. So with that in mind, let's try and do it. There's 4 different functions that this guy might have in mind. He might, for example, be thinking of the function that does nothing to your inputs. So if you put in 0, you get out 0. If you put in 1, you get out 1. Or he might be thinking of the one that swaps them. So if you put in 0, you get 1. If you put in 1, you get 0. Or it could be one of these 2 constant functions, where no matter what the input is, you get a 0. Or no matter what the input is, you get a 1. So those are the 4 different functions. The question he wants you to answer is not which of these 4 functions is his secret function. That would actually be too hard a problem for the quantum computer to solve. Instead, what he wants you to find out is whether the function is one of these balanced functions, so like f1 and f2. It's called balanced because half of the outputs are 0 and half of the outputs are 1. Or whether they're constant functions like f3 and f4, because both those outputs are the same. This seems like a really easy problem if he lets you use his computer at least twice. You would first send in a 0, and then let's say you got the output 1. And then you know that, it's one of these two. And then you'd send in a 1, and if you got the output 0, then you'd know it's F2, and so you know it's balanced. On the other hand, if you got 1, you would know that it's F4, and so it's constant. So it seems like a really easy problem as long as he lets you use the computer twice. But that's the catch. He's not going to. He's only going to let you use it once. Can you still solve this problem? The answer for a normal computer is no way. But what about if you have a quantum version of this same puzzle? Can you solve it with a quantum computer? Well, first he has to actually make a quantum version of this puzzle that's fair. Pretend with me for a moment that we are that guy. So we need to come up with a way of doing our computation that is going to be kind of fair for the quantum computer. What I mean by that is that the quantum computer isn't going to be able to act in the exact same way. Its input is going to be a qubit. So, that's going to be some light. The light is going to shine into the computer. And then the output is also going to be some light. So we need something that will do the same kind of computation, but is able to be encoded in light. So I'm going to show you one way that we could make that happen. And at first it's going to seem really strange. This strange computation you're about to see me make, that is actually possible to make directly from the original classical computer. So if this challenger wanted to, he could just give the classical computer to the quantum person, and then the quantum person would have to do the work to convert it into a quantum version. And it is totally possible. It's just a bit of a pain and a little bit mean. So instead, we're going to pretend we're a nice person, and we'll make something that encodes that function for them. So that is what we're trying to make right now. Quantum version of f. Well, let's just say, for example, that the secret function that we want to encode is f2. So 0 goes to 1 and 1 goes to 0. So that is a balanced function. So how are we going to go about making our secret version of f2? First, I'll give you the sort of theoretical version of it, and then you and I both are going to have to figure out how to actually make it in this experiment. Remember that there are two different outputs that could be coming out of this laser. One type of light that it can output is what we're going to call horizontally polarized light, or 0. So we'll write it like that. And the way to make it is to put a filter on this light like this. And as long as the filter is aligned this way, then all of the light that comes out is going to be horizontal. So that means light that's oscillating in the horizontal direction. And there's also light that is in the one state, which is light that's oscillating in the vertical direction, so up and down. What we want is both the 0 and the 1 inputs to get converted in some way according to what function we have. The most obvious thing to do in this case is have the 0 light become the 1 light and the 1 light become 0 in this case. Unfortunately, though, that's not going to work, because if this box is going to be made of quantum parts, it actually just can't operate this way. The reason is a bit technical. It's because quantum processes have to be reversible, and sometimes this scheme won't be reversible. It's not important though, because we can overcome this inconvenience pretty easily and still encode the function that we want. So this is the way we're going to do it. You see here, we've got 0 and it goes to 1. Whenever anything goes to 1, what we're going to do is take the original light and flip it. So this is what I mean. So here's the light coming out in the 0 state. And what that means is if you had an electron in the way, that it would first get bumped upwards, and then as the light moves along, it would eventually get pushed downwards and then back up. So this electron would be bouncing in this direction. But crucially, originally it gets pushed upwards. Now, what if I flip this light upside down? Then what would happen first is that the electron would get pushed downwards. So it would still oscillate up and down, but it would first go downwards. So that is a different type of light, very subtly different, but this negative version of the light is one that pushes in the opposite direction first. So whenever the output is 1, we flip the light. On the other hand, the 1 input goes to 0, and the way that we're going to encode that is nothing happens. So the 1 just gets to go through exactly as it was. So in other words, if we had this light coming through, it just goes through as if nothing happened. So this action is what we need our secret quantum computer to do. Remember, we're still the guy right now. So that's what we need to figure out how to do. Just so you see how this works, if we had another function, if we had f4, it would be 0, 1, and both of those go to 1. What would happen is that, okay, well, this bit is still the same. The 0 goes to 1, so 0 gets flipped. But now 1 goes to 1 here, and so it needs to get flipped as well. So 1 will go to -1. So if f4 was our secret function, then that is what we would need our computation to do. All right, so that's all good in theory. This is the part that I understand well, but now we're going to have to figure out how to actually do this. I got this stuff that I am really excited about. I don't actually know how to pronounce this. 1 lambda? I don't know. You know how you say stuff like, oh, a half wave plate or a quarter wave plate? This is a full wave plate then, I guess. Right, this is what it does. It takes any light and it flips it upside down. So whether you have a 0 coming in or a 1 coming in, it flips it upside down, which incidentally is exactly what we need for F4. So that's cool. We figured out how to do F4. So in the case of F4, if that was this guy's secret function, then he'd just put this here. That would be it. I don't think this is right, actually. I think I'm getting confused about what these wave plates do. Nope, I was right the first time. That is how you make F4. But then I spent 40 minutes confusing myself. That and that, you get vertical light. I have no idea what I was talking about here. Eventually I decided to just do an experiment to find out what the wave plate does. Easiest way to tell if it is right is to actually do this full experiment. So maybe that's kind of good. Just putting this thing here because I want to protect this polymer. It's not really rated for using lasers, and I don't want to burn a hole in it. It was very, very painful to watch myself struggle through this experiment, so I'm going to summarize this bit for your sake. First, I tried putting this light through the quantum computer without the wave plate in the way, and I did a bunch of measurements of that light using a filter, which I tried orienting in a few different ways. So far, so good. Then I put the wave plate up and I tried the same measurements. And you'd expect some sort of change in the outcomes, right? Because after all, the wave plate is meant to change the light. That's the point. But strangely, all of the results were exactly the same as if the wave plate wasn't there at all. What? So in other words, nothing has happened here. So what I'm going to guess is that this plate, the one that I have here, is the one that just takes anything. So whether that's 0 or whether that's 1, it takes it to the negative version of itself. The thing is that if you have something that does that, it just takes absolutely any light to the negative version of itself. That's very hard to detect that change in the light. So the difference between light that's coming in at 0 and -0 is very, very difficult for us to detect. It won't work to just use one of these because remember, like 0 light is horizontal light and -0 light is also horizontal light, but it just starts in the other direction. This filter just filters any light in horizontal direction. So whether that's 0 or -0 doesn't really make a difference. And so that's, I think, why we're getting these unobservable changes here. So yeah, that's kind of good. Like, we figured out what this plate does. It takes any light and it flips it. So if I had light traveling in any direction, like let's say this direction, it would become this light instead, which, yes, again, is very, very hard for us to detect. So that means that we were right earlier. This is F4. So F4 is the function that takes 0 to 1 and 1 to 1. The behavior we want for the machine that represents a function is that whenever the output is 1, it flips the light. And because the output is always 1 for F4, it should flip any light coming in. So, okay, great. This is F4, I'll label it, and we can stop worrying about it. Okay. Now let's figure out how to make F2. Okay, remember that if I wanted to send in 0 light, I put this little filter in this direction, whereas if I want to send vertical light, then I have to put it in this direction. But as you can see, that opens up the possibility of putting it in any direction. Why don't we put this in at 45 degrees? All right, so this light is originally this 45-degree light, which, by the way, I'm going to start calling plus. It's the conventional notation. I don't love it, but that's fine. So plus is equal to a bit of 0 and a bit of 1. But remember, we can just think about those two components separately. So we can think about the 0 component and the vertical component as kind of like separate entities, and then we can think about what happens when you add them back together. So both of these are coming out of the laser in equal amounts. And then what this polymer is going to do is it's going to slow down both of them, but it's going to slow down the vertical component more than the horizontal component. And so they go out of sync with each other. The vertical component should be up to here instead. Now we have light that's pointing up and to this side. So the combination is as if we had light pointing this way, which I can show you on a little diagram. So originally we had the vertical component of light, which I'll call 1, and we had the horizontal component of light, which I'll call 0. And when we added them together, we got plus, so the 45 degrees light. But then what happened when the light went through the polymer is that this light got slowed down quite a bit. So when it should have been pointing upwards, it was so slowed down that it was actually pointing downwards instead, the negative version of the same vertical light. All right, so that's what's happened to those two components, but what's the new sum then? If you have some light that is pushing an electron this direction and downwards, the total is as if it's pushing like this, which we call minus. Again, I don't really love that, but that is the convention. So 0 minus 1 is what we call minus. That's what's coming out. So you had this plus state originally where both the horizontal and vertical components are exactly in sync with each other. After the polymer, just the vertical component gets slowed down. And so it's as if you have this minus light instead, where they're a little bit out of sync with each other. And the way that I can tell that that's what happened is because if I had the plus light, then what should happen is when I do the measurement aligned with the original direction of the filter, then we should get most of the light going back through. And instead, when I put it at like 90 degrees to that, I should get most of the light get cut. On the other hand, if I had minus, it's the opposite, because minus is pointing this way, and so 90 degrees to plus. And so if I have the filter aligned with the plus, instead I should see most of that light get cut out, because that's 90 degrees to the minus. And let's see, if I put it in like this, you can see that pretty much all the light gets cut out when it's at the 45 degrees. So that is exactly what you'd expect. And if I put it here, you can see that most of the light goes through. And so that tells us that this light that is coming through this polymer must be in the minus direction, which is great news. So we've designed F2. We're almost done with our work, but we have 2 more functions to go, and they're really easy at this point. Just write a little label telling me that when I orient it this way, this is F2, okay? But making F1 is going to be really, really similar, because here, this is F2, at least when it's oriented this way. But I'm pretty sure you can make F2 really, really easily now, because if I just swap this, the direction, I think it's going to do what we want, because remember originally we said that this thing was slowing down stuff in the vertical direction but not as much in the horizontal direction, right? But if I just flip this over, now this is still the slow direction, but now that's aligned with the horizontal axis. And so if I put that in here, the slow direction is now the horizontal part. And so this goes slowly, whereas the vertical part goes through fast. And so there's still a lag between them, like they're still out of sync, but it's going to be the horizontal that lags, the vertical that goes through without any problems. This is basically the same as what we had before, but if we draw this on a little diagram where we had 1 here, 0 here, and the 0 is going to go to here instead now, so this is -0. We originally had plus, and it's going to become this thing. But if you think about it, this thing is very similar to that other result we got, which was called minus. It's exactly the same as minus, but in the opposite direction, flipped. And so it's just minus, minus. So this output is basically minus. It's not going to really look different to us when we try and detect it with this filter. So remember, if I put this filter in here at the 45-degree angle, then it does nothing. Whereas if I put it after the polymer, you can see it cuts out quite a lot of the light. On the other hand, if I put it at 90 degrees so that it lets through most of that light. So like before, this piece of polymer is doing exactly what we want, but we just have to orient it in a slightly different direction. This is F3. Sorry, F1. This is F1. Okay, cool. So this little thing is F2 and F1, and this was F4. All right, one last one to do, and thankfully this one is really easy. F3 is the one that takes 0 to 0 and 1 to 0. And remember, if the output is 0, then you do nothing. So in other words, for the 0 light coming in the horizontal direction, do nothing to it. For the vertical light that's coming in like this, do nothing to it. So in total, do nothing. In other words, if our secret function is F3, then you will put this box here, the super secret box, and the person who has the quantum computer and needs to solve the challenge will probably think that there's something in here, but unbeknownst to them, there actually isn't. It just hit me that, like, I am right now trying to make a real quantum computer with real quantum gates in it. Like, that's so crazy. I mean, how nuts is it that I studied quantum computing for so many years and I never did anything like this? Like, I never actually tried to build anything. And so I had like no appreciation for this and how much work it is. I had the idea to explain the Deutsch-Jozef algorithm on my YouTube channel ages ago, but it really didn't occur to me that I would actually be able to show it to you. This is really cool. Okay, so now the role of the stranger is pretty much done. They're just going to come around and put down their super secret quantum version of F, and we won't know what's inside. It could be this oriented this way, or it could be this one, or it could be nothing at all. We don't know which of those 4 possibilities it is, and it's going to be inside of here. Now, you and me have to try and solve this problem by making a quantum computer around this quantum box. We pretty much actually solved this problem when we were trying to figure out how to make this thing, but let me explain anyway. There are these 4 functions, and we don't know which one of them is going to be represented by the box, but we just have to be able to use our quantum computer one time to figure out whether it's one of these 2. So these are the balanced functions, or whether it's one of these 2. They're the constant functions. So let's think about how you might do it. One way is just to send in a 0 state and figure out what comes out on the other end. So it could be a 0 or a -0. If it was a -0, then it must be that the output is 1. So 0 goes to 1. So it's one of these two. It's either F2 or F4. But that's not any good to us because then we'd be over with. Like we'd only get that one shot, and we sent in something that only narrows it down to F2 or F4, and that isn't enough to solve the problem. By the way, you might be wondering, if I sent in a 0, so horizontal light, and I got negative horizontal light, so -0, would I even be able to tell that something had happened to the light? The answer is you wouldn't be able to tell using a filter. Like a filter can't tell the difference between those two, but it is actually possible to tell the difference between them. I used to think it wasn't. Like in theory land, we kind of treat these two things as if they're the same. We say that they're off by a global phase and global phases aren't measurable, but that's not true. In theory, we always just pretend that there is no way to tell the difference between these two. But the way to do it is to use a beam splitter and then do constructive and destructive interference experiments on the two branches afterwards. It doesn't really matter. I'm just pointing that out because it was very interesting to me to realize that this is true. But anyway, not important because this scheme isn't very helpful. Just sending in a 0 is only going to tell us a little bit of information and not the information that we need. The same thing if we send in a 1. If we get, for example, -1 out, that's no good to us either because, well, that means that 1 goes to 1. So it's either this one or this one, so F1 or F4. But I mean, again, we don't know whether it's balanced or constant, and we've wasted our one turn of using this secret machine. So we need to do something more clever. So like we were doing a little bit earlier, why don't we put this in at 45 degrees? All right, remember that 45-degree light is the combination of 0 and 1 light. Let's pick one of these 4 functions to be the secret function in our example. Maybe let's make it F1. So F1 takes 0 to 0, so 0 just does nothing, whereas it takes 1 to 1, which means that the 1 component picks up a phase. So it gets flipped. So instead of having 0 plus 1, we have 0 minus 1, and that is a different state of light. A very special quantum thing has happened here. If we were just sending in either 0 or 1, we only get to find out what it does to one of the inputs, right? Either the 0 input or the 1 input. But if we put in the 0 plus 1, it exactly encapsulates what the function does to both 0 and 1. So in other words, this state does actually contain all of the information about exactly which one of these 4 functions it is. F1 does this to that input. And I'll just quickly write this out, but depending on what this function is, it will send this state to one of these 4. And if you can figure out exactly which one it is, then you'd be done. You would know exactly which function we're dealing with, and so you could tell whether it's balanced or constant. But if you try and figure it out the naive way, which is just by measuring the state in the 0 or 1 basis, so if you put this filter down like this, what are you going to get? In all of these 4 cases, the light is an equal combination of horizontal light and vertical light. The difference is just how in sync or out of sync they are. But the filter will only tell you what fraction is horizontal and what fraction is vertical. And so in all of those cases, it's going to say that, half of the light is horizontal and half of it is vertical. So no matter what the secret function is, this measurement is going to cut out 50% of the light. And so seeing that is completely useless to you. And this is a general thing, by the way. So with quantum computing, you might think it's super powerful because if you have some function that you want to calculate on a whole bunch of inputs, you can put in a superposition of these inputs. So you can do 0 plus 1. And if there were more inputs, you could do a superposition of all those inputs, and you can send it into your computer. And the quantum computer will genuinely do that calculation on every single one of the inputs. And your state, your final state, will be a superposition of those outputs for all of the possible inputs. But then if you go to measure it, what's going to happen is that it's just going to collapse to one of them. So instead, with a quantum computer, what you have to do is you have to take all of those inputs and find a way of cleverly combining them such that when you measure, now you're going to just get out the bit of information that you wanted. And this is super, super tricky most of the time. And I mean most of the time, it's not possible. Or at least maybe it's possible, but we definitely haven't thought of it. And it's very, very, very likely that it's not possible. But this is an exception. In this case, it is all going to work out for us. The way to do it is exactly what we saw earlier, where, say, this is my secret function. This is f1. If I orient it like this. What this does is if the light is from f1 or f2, then the light is going to have gone from being oriented in this 45-degree angle to being oriented like this, or the negative version of that. And so that means that if I put the filter in this direction, it should all just go right through. Whereas if I put it in at 45 degrees, it should get cut out. So let's just do the measurement in that direction. So I'm going to put this in at 45 degrees. And you can see that indeed it cuts out most of the light. So we can be pretty sure that the light is coming in at this direction. On the other hand, let's say the function had been f3. Well, then the light was coming in at 45 degrees originally and nothing happens to it. And so if I put the filter on like this, in the same measurement, it should do pretty much nothing to the light. And that is what we see. If we put it in at the opposite, it should pretty much cut it out, which it does. So that is what will happen to f3. If we have f4, what it does is it turns light that was 45 degrees into light that is the opposite, which is pretty much the same. It's going to go right through this filter regardless. And you can see that that is what happens when I put it in at 45 degrees, whereas when I put it in at 90 degrees to that, it cuts out almost all the light. The upshot is the only measurement you'll need to do is to turn this filter at 45 degrees.
And that's how you solve this quantum riddle using the Deutsch-Jozsa algorithm. First, you send in plus light, and then you measure the output at 45 degrees.
To prove to you that you know how to do quantum computation now, I'm going to be that guy and I'm going to challenge you to a game. So I'm going to put down a secret function in here and I'm going to let you see what happens when I put this filter in at 45 degrees. And from that, you're going to have to guess whether my secret function was a balanced or constant function. So my secret function is ready now. I'm going to put this filter in at 45 degrees. And that cuts out most of the light. Whereas if I put it in here, essentially no change. So is my function balanced or constant?